This is an overview of discrete and continuous distributions in probability. The first thing for us to know is the definition of a random variable. A random variable is a variable whose value is determined by chance. An example would be flipping a coin 3 times. And then letting x, our random variable, equal to the number of heads. So in this case, if we get heads, 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 our random variable will be equal to 3. But if we get a heads, and a tails, our random variable x will equal to 2. But the idea is, until we flip the coin, we don't know what our x is going to be, and in fact, it is a chance variable. It's not something we can determine in advance. Random variables are denoted by an uppercase letter, whereas their numeric values are denoted by lowercase. The next three topics, density function, cumulative distribution functions, and expected value, are topics and concepts that you should become very familiar with and not have to look up. It's something that you really need to know. It's your basis for what you're going to learn, and if these things come to you quickly, naturally, and they're in your memory, other things will fall out for you quickly. Next, we will discuss moment generating functions, which are related to expected value, and then we'll do particular examples of discrete distributions and particular examples of continuous distributions. The density function tells you the probability that random variable x, denoted with a capital, takes on a certain value little x. For discrete functions, this is fairly straightforward. Either you have a formula p of x, which then you plug in a value of x, and then you get the probability. Or you have a table where you look up a value of x, and it'll tell you the probability that your random variable x takes on the value of little x. For continuous random variables, we think of random variable x being able to take on values of a portion of the real number line, but of course any part of the real number line has an infinite number of values. And since there are an infinite number of values, the probability that x takes on any one particular value, such as a, is infinitesimally small. So in other words, we usually don't ask what's the probability random variable x equals a, because the answer would be 0. It's so infinitesimally small, it basically in the limit it's equal to 0. So what we do is we ask what's the probability x is between a value a and b. Then with this, our density function is a function that tells us the probability that random variable x takes a particular value, even though we don't usually plug in one value and give an answer. Instead, what we do is we integrate the probability of x being a value between a and b. So we sum up all of these probabilities, and that is what this formula here is here. The probability that random variable x is between a and b is equal to the integral of f of x between a and b. And here's an example that we had talked about before. We were talking about flipping a coin 3 times, and this is the sample space. These are all the possible outcomes for 3 coin flips. We could get heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And when you need to make a list like this, I find it is convenient to think of h's as zeros, t's as ones, and then this is just counting in binary from 0, 1, 2, up to 7. So let's let our random variable x equal to the number of heads. For now, we're going to focus on finding the density function. We list the possibilities for random variable x. So x can equal to 0, x can equal to 1, x can equal to 2, and x can equal to 3. So the probability x equals 0, that's 0 heads, that can happen one way, and that's if there's all 3 tails. And that is 1 out of 8 possible outcomes, so the probability is 1/8. The probability that x is equal to 1, so I have to look where there's exactly 1 heads, and that occurs at tails, tails, heads, tails, heads, tails, and heads, tails, tails. So that occurs 3 out of 8 possible outcomes. So 3/8 is the probability. Similarly, you can see that probability x equals 2 will be 3/8, and probability x equals 3 is 1/8. An important thing to notice is once you've listed all the possible values that x can take and you calculate the probabilities, when you add them up, you should get equal to 1. If it's less than 1, you've probably missed a case. If it's more than 1, then something has gone wrong and you need to double check. Sometimes probabilities are listed in a table format like this, where you can read the probability that x is equal to 0 is 1/8. The probability random x is equal to 2 would be 3/8. So the values the random variable can take is on the first line, the probabilities is on the line below. I'm also going to do this graphically because one, sometimes that's the way it's presented, but I also feel like this will help us with our next problem. So what I do is I list the values that random variable x can take. That would be 0, 1, 2, and 3. And then I draw this axis here is the probability that x is equal to that value of x. So the probability that random variable x is equal to 0 is 1/8. The probability random variable x is equal to 1, well, that's 3 times as high over here at 3/8. Probability random variable x is 2 is 3/8, and the probability random variable x is equal to 3 is 1/8. I'm going to use this graph to tell you how I think of cumulative density functions, and then we'll formally define it on the next slide. But here is how I think about it. I think about walking along this graph from the left to the right. And as I go, I pick up density. So I'm over here, and there's no density to pick up. So before 0, I'm at 0. And then once I hit 0, I accumulate 1/8. And I think of accumulating, which reminds me of the word cumulative, so that's how I kind of remember it. So I've accumulated 1/8. I continue walking until I hit the 1, and now I pick up, or I accumulate, another 3/8. So far I have 1/8 plus 3/8, which is what? 4/8, which is 1/2. I continue walking. When I hit 2, I accumulate 3/8 more. And then finally, when I get to 3, I accumulate 1 more 8th. And at this point, I have 1. So I can keep walking, but I'm not going to be able to accumulate anymore. I've already hit the maximum, which is 1. And you can think of this as picking up prizes as you go. So when you start, you have no prizes. And then when you hit 0, all of a sudden you find 1/8 of the prizes, or 1/8 of the cash money, reward, or whatever it is. And you keep going. When you hit 1, you've picked up another 3/8 of the reward. You keep going to 2, and you pick up another 3/8. You go to 3, and you pick up 1/8, and now you've picked up 100% of the reward. So you can continue on knowing that you've already maxed out. You've collected the entire reward. Now that we've kind of gotten an idea of what cumulative distribution is, here's the formal definition. And this is something you should know really well. It's something you should be comfortable with. Again, the sooner you get comfortable with this, the easier later things will come to you. So for the discrete random variable, big f of x, so this is the cumulative distribution. So little f of x is your density function. Big F of x is your cumulative distribution. So big F of x is equal to the probability that random variable x is less than or equal to x. And to find this probability, you are going to sum up all the probabilities that x goes from -infinity up to the value x. So that's the idea of picking up all the, or accumulating all the probabilities between -infinity to x when we were walking along the line. For the continuous, it's totally analogous, except now you're going to integrate from -infinity to x, and then t is your variable of integration. Another kind of analogy for you for cumulative distribution is you can think of this as like Pac-Man, and he's eating dots. And whenever he eats dots, he gets to keep it. That's like when you go and you're picking up probabilities. So he's coming along and he's eating the dots, and even when he dies, he gets to keep those dots. And you know those high point fruits that Pac-Man sometimes eats? That was like eating the 3/8 probability. It was like a really high probability, or very dense, so it's nutritionally dense probabilities. Oh, but the sad thing is here when Pac-Man is coming up to the ghost, he doesn't get to turn around and go back, not in our cumulative distribution Pac-Man, so that's kind of sad. And actually, he's actually just one-dimensional. He doesn't even get to turn away and go up because our cumulative distribution, is only one direction. But this story is not a tragedy, so there are no ghosts. And what Pac-Man gets to do is he gets to keep accumulating until he gets 100%, and then he's won the game. So now I can come back to my coin flip probabilities, which I guess isn't as interesting as Pac-Man, but this is what we've got, okay? So we have the probability, our density function, which I've written with the lowercase f to remind you the lowercase f is density function. F of 0 is the probability that x is equal to 0, and that's equal to 1/8. F of 1 is probability x is equal to 1, and that was 3/8. Probability x is equal to 2 was 3/8, and probability that f was equal to 3 was equal to 1/8. Now I can plot out my cumulative distribution. So I look at the f of 0. That is the probability that x is less than or equal to 0. So less than or equal to 0 is equal to 1/8. And anything smaller than 0, by the way, f of -1 is going to be equal to 0 because there's no probability until we hit 0. Then the probability that x is less than or equal to 1, well, I have our 1/8 plus our 3/8. The probability cumulative distribution function that x is less than or equal to 2 is going to be our 1/8 plus our 3/8 plus our 3/8. And then the probability that x is less than or equal to 3 is equal to 1. At that point, we've had all of our distribution consumed. Now I'm ready to plot my cumulative distribution. So I'm at 0 all over here until I hit 0, and then I spike up to 1/8. And then I continue at 1/8, and I stay at 1/8 until I get to 1, and I pick up another 3/8, so that puts me at 1/2. That's right here, my 1/8 plus 3/8. So now I'm at 1/2 until I get to 2, and then I can come up to 7/8. That's this point here. And I keep going to 7/8 until I hit 3. And now I am at 1, and I stay at 1 forever. Now we are ready to talk about expected value. And the thing you want to remember about expected value is that it is a weighted average, much like your grade is. So we sum up all your grades, and we multiply your grades times the weight. So if it's a test, it might be weighed more than if it's a homework example. So in this case, we're going to sum up all the values that x can take, and we're going to weigh it by its probability. So the expected value is the sum of all possible values random variable x can take times the probability that x takes that value. And so this is our expected value for discrete random variables, and for continuous, it's totally analogous. Instead of summing, we integrate, and then we just integrate x times the probability that x takes that value. Note, if you have a function of random variable x, such as x squared, or x squared plus 4, or x cubed, or x plus 4, the expected value of that function of x is just equal to that function of x times the probability of x. And there's the analogous situation for continuous. And then we have x to the n is just x to the n times p of x, or the analogous for the continuous functions. And because expected value is a linear mapping, if you have the expected value of x cubed plus 3x plus 2, so this is a function of x, you're plugging in your random variable x to make a function, you can separate it out. So that's the expected value of x cubed plus 3 times the expected value of 3x plus the expected value of 2. So the expected value of x to the third is just x to the third times probability that x takes that value. You can pull out the 3, and that's 3 times x times the probability of x. And then the 2, the expected value of 2 is just 2. An expected value is kind of what you would semantically or intuitively think an expected value. It's kind of a middle value, and in particular, it's a weighted average of all the possible values you can take. So things that are more likely weigh heavier, right? And then, of course, the things that are heavier or have more mass way more in this weighted average. We can come back to our coin flip example now and find expected value. And it's just each value that x can take. X can be 0, 1, 2, or 3. So we have 0, 1, 2, and 3. And then we multiply it times the probability it takes each of those values. So the probability of x equals 0 is equal to 1/8. Now we're on this line. The probability x equals 1 is equal to 3/8. The probability x equals 2 is 3/8, and the probability x equals 3 is 1/8. So we multiply these together, and then we sum them all up. The last thing we want to do is find variance, and so we will go back to our slides to get the definition of variance. Here's the formula for var x. That's the expected value of x squared minus the expected value of x squared. So to get var x, I need to get expected value of x squared. So I take my values of x, which is equal to 0, 1, 2, and 3, and I square them. So I have 0 squared, 1 squared, 2 squared, 3 squared, and now I need to multiply the probability that x takes that value. So the probability x is 0 is 1/8. Probability x is 1 is 3/8. The probability x is 2 is 3/8, and the probability x is 3 is 1/8. So to get var x, I take this, whatever this sum ends up being, minus this sum squared. I have one last problem to go with this coin flip example, and that's to use the CDF to find the probability that x is greater than 1, but less than or equal to 3. So if I didn't have to use the CDF and I could use the density function directly, I could look for where probability of x is greater than 1, and that's these two cases, and also both of those two cases, x is less than or equal to 3, so I would add 3/8 plus 1/8, and that would give me 1/2. But I do want to use the CDF because I need to practice using the CDF. So I want to look at my cumulative distribution function at x equals 3, and just to remind myself, that's the probability that x is less than or equal to 3. So I plotted this on this real number line here. X includes the number 3, which is why the dot's filled in, and it's everything less than or equal to 3. So I put my f of 3 in a green box to remind me that's this green shaded region. And now, since I'm looking at probability over here in my problem statement, that x is greater than 1, so I've looked at x at 3, I'm going to look at the cumulative distribution function at x equals 1. So f of 1, now I'm down here near my graph, is equal to the probability x is less than or equal to 1. So it's everything including 1, and then everything to the left of that. So I put this on my real number line in yellow next to my green line, and I put a box around my f1 to remind me that's where I'm at. Now looking at my problem statement, and I put this area in red to remind me this is about x being greater than 1 and x less than or equal to 3. And that's exactly this region here. I want to include 3, which is why I filled it in. And then I do not want to include 1, which is why I put the little bubble, the empty bubble at 1. And if you look at that, that is exactly this green region minus this yellow region. And now I'm ready to answer my question. The probability that x is greater than 1 and less than or equal to 3 is equal to f of 3 minus f of 1, which is equal to, if I look at 3, my cumulative distribution is at 1, and at 1, my cumulative distribution is at 1/2. So I get the same answer, which is 1/2, which is the same as if I added the probability densities of x equals 2 and x equals 3. So the key to this problem is using these endpoints, kind of graphing it out, and then you can figure out which, it's usually, right, the 3, where you have the bigger distribution, minus the cumulative distribution at the smaller number. So those are the 3 main ideas for density functions, cumulative distribution functions, and expected value. And these are ideas, or these 3 things are things you should be really familiar with so you can move forward successfully. You're just going to be seeing this all over the place. The examples we've done so far have been in the discrete, but we will do some continuous examples in just a moment. I did decide to do the moment generating function as a separate video. It is very useful, but other things don't necessarily fall out from it, so I kept it as a standalone video. And now we'll get to those continuous examples I had talked about. Our first continuous example, we have this function f of x is equal to 12.5x minus 1.25. X ranges between 0.1 and 1.25. We want to find the probability that x is between 0.2 and 0.3. We want to find the cumulative distribution function, and we want to find the expected value. To find the probability that x is between 0.2 and 0.3, I'm going to sum up the probabilities for the values of x between 0.2 and 0.3. Or actually, because it's continuous, I'm going to do the analogous version of summing up, and I'm going to integrate. I set up my integration, and so I'm going to integrate between 0.2 and 0.3 because that's where I want my values of x to be, and I plug in my function f of x, which is 12.5x, minus 1.25. That's my probability function. So I'm integrating my probability over all possible values of x between 0.2 and 0.3. The rest is integration and plugging in, and I get my answer here, 0.1875. I have my formula for cumulative distribution here, so f of little x is equal to the probability random variable x is less than or equal to little x. For continuous functions, or continuous random variables, that's the integral from negative infinity to x, f of t dt. And the t is just our variable of integration. Plugging in our particular example, our density function is equal to 12.5t minus 1.25 dt. And again, we replace the x with t because our limits of integration are going to be between negative infinity and x. So we just wanted a different variable here other than the variable x we're using. One more point to note. I did add this note here that f of x, our density function, is equal to 0 for values outside of x of 0.1 and 125, which was what we had in our original statement. So we actually we're going to be integrating 0 until we hit 0.1. So instead of negative infinity, we're going to start at 0.1. And then we're going to integrate up to x because we want the probability x is less than, random variable x is less than this little x. So this is the little x here as our limit of integration. And from there, it's just integrating, and again, we have our x here, which gets plugged in after we integrate, and we have our x squared. So for a given value of x, we can find the probability that random variable x is less than or equal to x, and you plug in your value of x here, and that will give you the probability. That it's less than or equal to x. It's easy to forget, especially if you have a difficult integral. This wasn't particularly difficult, but if you have a long integral, to remember that you have to write the CDF. So you have to write the cumulative distribution function. So I did write f of x. So for anything less than 0.1, it's equal to 0. Then it's the function that we found here for x between 0.1 and 0.5. And then once we've gone all the way from 0.1 to 0.5, we've accumulated all the density that we're going to have. So it's equal to 1 for x greater than 0.5. Last, I have the problem of finding the expected value. So I wrote the expected value equation here, and essentially you're looking at all possible values of x, and you're multiplying or you're weighing it by its probability. So we're going to go from 0.1 to 0.5 x. We put in our density function, 12.5x minus 1.25 dx. And from there, I trust you can do the integration and plugging in. Part 2 of this video is a totally separate video, and it goes over particular distributions for discrete and continuous distributions. For discrete distributions, we will look at geometric, binomial, and Poisson distributions. For continuous distributions, we will look at uniform, gamma, exponential, chi-square, and normal distribution. There is another short, pretty easy topic called Chebyshev inequalities. I have a separate video for that. For the remainder of this video, I will do a few more examples of the density, cumulative distribution, and expected value. Our first example, consider the random variable y is the number of cells exposed to an antigen carrying lymphocytes in the presence of polyethylene glycol to obtain the first fusion and gain immunity. I kind of didn't really understand that, but I will underline what I think is key. The random variable y is equal to the number of cells needed to obtain the first fusion to gain immunity. Under these circumstances, the probability a given cell will fuse is 1/2. And then, thus, the probability it will not fuse is also 1/2. It is reasonable to assume that the cells behave independently. The possible values for y are 1, 2, 3. In other words, it could be one cell before it obtains the first fusion, or maybe you need 2 cells before you get the first fusion, or maybe you need 3 cells, so basically just integer numbers. What is the probability density, and what is the probability p of y is greater than or equal to 4? We know probability y equals 1, or our probability density is equal to 1/2. They told us that. If we want the probability y equals 2, that means the first cell does not fuse, so it takes 2 cells before we get our first fusion. So the first cell does not fuse, but the second one fuses. So the probability the first cell does not fuse is 1/2, times the probability the second cell fuses is 1/2, so we get 1/4. The probability y equals 3 is the probability the first cell does not fuse and the second cell does not fuse, but the third cell fuses, so that's 1/2 times 1/2 times 1/2. This is the first cell not fusing, the second cell not fusing, the third cell fusing, that's 1/8. If you look at this pattern, you won't be surprised, but our density function then, the probability that of any value y is equal to 1/2 raised to the y power, where y is equal to positive integers. It's 0 everywhere else. If someone asked you to show this was a probability density, you would have to additionally need to show that the sum converges to 1. Remember, when you sum up all the probabilities, you should get that equal to 1. And to do that, you're going to use this formula for convergence of a geometric series, where a is equal to 1/2 and r is also equal to 1/2. You'd plug it in, you'd show that it converges to 1. But that was an aside. We should go on. We need to find the probability that y is greater than or equal to 4. That was the rest of this problem. The easy way to do this is the probability y is greater than or equal to 4 is equal to 1 minus the probability y is less than or equal to 3. And here I've said that would be equal to 1 minus probability y equals 3 minus probability y equals 2 minus probability y equals 1. I plug in, and my answer is 1/8. The next example, a drug is used to maintain a steady heart rate in patients who have suffered a mild heart attack. Consider the hypothetical density given in this table for x, the number of heartbeats per minute obtained per patient. What is the average heart rate of all the patients receiving this drug? This is just the expected value problem. It's the weighted average. So I'm going to take each value of x, the 40, the 60, the 68, the 70, the 72, the 80, and the 100, and multiply the probability that each of these occurs. And that will give me, and then I sum it all up, and that will give me my expected value. Next is a quick expected value problem. If the expected value of x is equal to 9, and the expected value of y is equal to 3, find the expected value of 4x minus 2y plus 6x. Now, expected value is a linear function, so you can separate them out. Expected value of 4x minus expected value of 2y plus expected value of 6. And then you can pull out your scalar multiples, so 4 times expected value of x minus 2 times the expected value of y plus expected value of 6. So now it's 4 times expected value of x is equal to 9, that was given to us, minus 2 times the expected value of y, which is equal to 3, that was given to us, plus 6, the expected value of any constant is just that constant. So that's this example. Next is a continuous example. The lead concentration in gasoline currently ranges from 0.1 to 0.5 grams per liter. What is the probability the lead concentration in a randomly selected liter of gasoline will lie between 0.2 and 0.3 inclusive if the probability density f is given by f of x is equal to 12.5x minus 1.25 for x between 0.1 and 0.5 and 0 elsewhere? So the 0.2 and 0.3 lie within these ranges, so you can just integrate from 0.2 to 0.3 the function, the density function, dx. And if you do all the integration and plugging in, you should get 0.1875. Now, if additionally we want to know the cumulative distribution function, we're going to use the definition of the cumulative distribution function f of little x is equal to probability that x is less than or equal to little x. Again, because we're accumulating all the probabilities up to x, and again, this is something you should know really well, and then that's equal to, and this relationship you should know really well, you would integrate between negative infinity and x f of t dt. Integrating, actually, since f of x is 0 until we hit 0.1, we're going to integrate from 0.1 to x, our function with the t replaced. Then I integrate, and I have my two values to plug in. And I simplify this. Plug in x squared, and I get this. Plug in 0.1 or 0.01, and I get that constant. And then last, and don't forget to do this, you really need to write out the entire cumulative distribution. Before we hit 0.1, we have no probabilities. Between 0.1 and 0.5, we have this function, and then greater than 0.5, at that point, we've already collected all of our probability. And one last question, we already solved this over here. What is probability the lead in a randomly selected liter of gas will lie between 0.2 and 0.3, and we use the density function. But we can also solve this using the cumulative distribution function. So if I think about my number line, my cumulative distribution for 0.3 is the probability of 3 and less. My cumulative distribution of 0.2 is the probability of 0.2 and less. So if I want to know if it's between 2 and 3, I can subtract probability of the cumulative distribution at 0.2 from the cumulative distribution of 0.3. So I go ahead and plug in my 0.3 and 0.2 into my cumulative distributions. This is 0.3, this is 0.2, and I get the same answer as using my density, which is good. Last is to find the expected value of x, which I would do, I would integrate from negative infinity to infinity at x f of x dx. Again, all values of x times their probability, their weights, so 0.1 to 0.5x times f of x dx. And if you do all the calculation, it should be equal to 0.3667. And I want to mention you can also think of this negative infinity to infinity. If you don't like the fact that I only did it between 0.1 and 0.5, you can think of going from negative infinity to 0.1, but the function, the probability function, is 0 at that point. And then you go from 0.1 to 0.5 as we did, and then 0.5 to infinity also is multiplied by the 0 probability. And that's it for this video. As I said, our next video will pick up with examples of discrete distributions and continuous distributions. Thank you for watching.